All right, so welcome back. So I would let more people join and then we are going to start today's discussion. All right, good evening. And today we are actually moving to a different topic, moving on to a different topic today. And there are certain other aspects of control systems that we are going to discuss today. So this is going to be part 21. All right. And we are going to discuss transient response errors today. So again, I'm going to explain all the terms that I'm using right now. Okay. So actually, let me just change the title here. Transient response errors and system types. All right. So we had a bit of discussion in one of our laboratory classes regarding errors and everything. All right. So let's start our discussion with that notion. All right. And we are going to do a bit of programming today as well. Okay. All right. So we all already know about transient response, right? What do we call a transient response? Transient response is essentially transient. By that, transient state is essentially the states observed by a certain system between two steady states. So if a system is in off state, in that case we call that a steady state essentially. And after and for a stable system, okay, that can reach a steady state, then after the system has been on for a very long time, then that system also reaches another steady state, and everything that happens in between those, it's called transient state, right? Now transient response in essence is kind of a misnomer here. Okay, transient response, the term transient response not only talk about the transient states, but it also talks about steady states. So essentially this is kind of a misnomer. I should rather, instead of saying transient response errors, I should instead of calling this transient response errors, I should call this just time response errors. Essentially, transient response means that we are also transient response includes not only the transient states but also the steady state response. So when I say transient response, I also include the steady state responses as well. So essentially we are talking about time response, right? So here we are talking about time response errors and system types actually. But I named the topic transient response errors simply because of the fact that this is the name that you're going to find in many books really. So instead of calling it time transient response error, I'm going to call it time response errors, right? Because really transient response is not the response during the transients, but also includes the steady states and everything, or essentially the time response, right? Now, before I can talk about errors, we shall have to go back to the very first class we ever had. Okay, someone is asking a question. Oh, final project is Okay, someone is talking about a PID tuning tutorial using Python, right? And I am onto that. I'm going to do that. We actually had a private discussion on um, uh, designing a proportional controller using simple root locus technique and Python. And you have certain auto tune or PID auto tuning modules, right? In case you want to design an adaptive system where you would have auto tuning PID controllers, and that can be achieved using Python. In fact, in real time. So we are going to see to that. So don't worry about that. I'm actually in the process of making a tutorial on that, and I think this is going to be a useful tutorial, right? So many people who are trying to incorporate Python into their projects, and if you need a PID controller, how would you do that, right? So we're going to make a tutorial on that. All right. So right now we are talking about transient response errors or the time response errors. Now this is the topology of our control system, right? So we usually have a controller, right? We usually have a controller cascaded with a plant or a system or whatever you want to call it, right? And then that is actually fed back to this input here, to this comparator here, okay, by means of a feedback system. So we would have a feedback transfer function. Okay, so something like that we are used to. Now since these two are in cascade, I am going to, for the simplicity's sake, I am going to combine these two. These two are in cascade, so I am going to just combine these two into a single transfer function. So they would kind of look like this. They would simply become a single transfer function. I can do that, right? Because they are in cascade, so I can combine those two into a single transfer function. And that's the output of the system, and that is being fed back. So this is the reference input, and this is the controlled output signal, and this is the transfer function of whatever we had here. Yes, absolutely. The thing is, someone is saying in MATLAB Sibling you already have a PID tuning tool, but the problem is that if you want to incorporate it with other projects, like maybe you are doing certain things in robotics, that for that, if you are using Python, then in that case you'd have to use Python for your PID tuning and all, right? And if you are trying to implement some sort of a real-time system, in that case also you are going to probably use Python, right? And if you are trying to make a prototype system, in that case you probably cannot afford a MATLAB license, right? So you would have to use some other tool like Python as an alternative, right? And really, if you understand the theory of PID tuning and everything, it is not very difficult to implement really in any programming language. You can even do it in C++. Okay. All right. So this is the standard feedback system, right? So we had plenty of things here. We would probably have plenty of things here, and this might have some other things as well. So we're just taking a simple feedback loop here, right? And we know that this signal is known as the reference input. Let me just denote everything. So this is called the reference input signal. In fact, this signal is given in its Laplace transform form. Essentially, you can consider everything in time domain as well. And this is the output signal, okay? And also, instead of saying output, I'm going to say this is the controlled output, control variable, controlled output, or controlled variable rather. So this is the reference input variable, this is the control variable, and this is HS is the feedback variable. And here, whatever signal goes into this one, say let's call this this one, and this is a comparator, okay? This one is a comparator. So essentially, whatever feedback signal comes in, this comparator actually compares with the reference input signal. And here whatever signal comes out of this, so essentially RS minus BS, that gives you ES. This ES is known as the actuating error signal. Actuating error signal. Okay, we actually discussed all these things. All the proper nomenclatures have already been discussed in one of our earlier classes. Rather, the very first class, I think. In the greatest possible details, in my opinion. We discussed all this terminology, right? All right. And we also know quite easily that the total transfer function here, okay, we also know the transfer function here, and that can be derived very easily. Let's just derive it once more. Okay, so RS is going into this, and BS has been subtracted from that, so I get ES. So if I just write ES is essentially RS minus BS. But what is BS? BS is the feedback signal. But what is the feedback signal? That feedback signal is essentially CS times HS. So I can write this as CS times HS. Hold on for a second. That's fine. Anyway, I can write this as CS times HS, right? And that's fine. And this ES is actually fed into GS, and that outputs CS, right? So CS is essentially ES times GS. Okay. So we also know that CS is GS times ES, because if we just look at the GS block here, if we just look at the GS block, you will see that the input to this GS block is ES and the output is CS. So that's how we have this, right? But now here we already know the value of ES, which we can replace here. So if I put the value of ES, which is RS minus CS times HS, then we have this as GS RS minus GS HS CS, right? So that's actually equal to CS, right? And if we bring this term to the left hand side, so then and factor out CS, we would have 1 plus GS HS times CS, and that equals RS GS, right? What are the GS RS? Again, put your questions if you find something difficult to follow. And if we take the ratio of the Laplace transforms of the output to the input, and here the output is the controlled variable and input is the reference variable, then that's called the transfer function. Again, we assume zero initial conditions the moment we took Laplace transform. So here this very figure here assumes that we have zero initial conditions. All right, so that becomes again, this is sort of a very quick recap of what we probably did, what we did long ago, right? It's just a short recap. Yes. Saish, I think you mean you want to do it with Python, right? So I'm telling you, there are quite a few very fantastic and highly optimized modules in Python that can help you do that. And not only that, you can do very complicated control algorithms as well, right? You can very easily do H infinity control, H2 control. Okay, so those are from robust control terminology. You can do lots of adaptive control using Python. You can do various techniques of adaptive control. You can do that. Okay, you can also do neurofuzzy adaptive control. Okay, all those things can be very easily implemented, and in fact there are certain optimized libraries. You can do optimal control, right? You can design Kalman filters very easily. Okay, all these libraries are already there in Python, very heavily optimized libraries. In fact, just to tell you, okay, there used to be a Fortran library called Slicot, SLICOT. Just do a Google search. This was a Fortran library back in like 1980s, I think, developed back in 1980s, and that had all the control system modules built in. So whatever you probably needed to design a control system, okay, you would have those modules in this Slicot library. Just like you have LAPACK, okay, you have LeanPack, you have ODE pack. So these are some popular Fortran libraries that people have used for ages and people are still using without knowing that they are using these. Okay, so the moment you are doing some sort of linear algebra, okay, in MATLAB or maybe in Python, you are actually under the hood using LabPack. Okay, so the moment you are using NumPy, you are actually under the hood using LabPack. So LabPack is a heavily optimized linear algebra library. LinPack is also a heavily optimized linear algebra library. ODEPack is a heavily optimized ordinary differential equation solving library. Okay, and if you just look through those packages, you will see that there are kinds of ordinary differential equations that you have never even heard of. Okay, you would see that. And under the hood, whenever you are asking Python or MATLAB to solve for a differential equation, under the hood it's actually calling a Fortran function. Okay, so instead of forcing you to use the Fortran function, because using Fortran is slightly difficult, more difficult than using MATLAB or Python. Okay, under the hood those libraries actually are acting as wrappers to these packages. Okay, so just keep in mind, keep these names in mind. And these libraries are so optimized that they can be run on your mobile phones and they can also be run on supercomputers. Okay, those of who follow these stories on supercomputers, you know, people say, okay, top 500 supercomputers. How do people compare supercomputers? Okay, how do people compare supercomputers? How fast is a supercomputer? How do people compare that? People compare those the capabilities of supercomputers by simply looking at the lean pack performance. How fast um, the supercomputers are able to compute things using LinPack library. So do linear algebra problem, extremely huge linear algebra problem. Okay, so these packages are so scalable in nature, right? You can run them on your mobile phones and they can also be run on supercomputers very efficiently. Okay, so Slycot is the Fortran library and its Python wrapper is known as Slycot, SLYCOT. It has optimal control libraries, it has robust control libraries, uh, it has many other state variable related control design packages. So pretty much everything that you, and of course including PID control, anything that you can imagine. Okay, it's there in this library actually. And the developers of the Python control system library are also the developers of the Slycot library. So that's something for your information, right? So this is again the closed loop transfer function. We call that a closed loop transfer function. Now here, this is the closed loop transfer function, this thing. Okay, right? Closed loop transfer function. Now here there are a few terminology. So here we are calling this to be the closed loop transfer function. This is CS by RS, which is GS by 1 plus GS HS. That's called a closed loop transfer function. But this term here, so this is called the CLTF. In just short, it's called CLTF, closed loop transfer functions. Transfer function. I think you will remember the name, right? Then this GSHS, this thing is called the loop transfer function. Just keep that in mind. It's called the loop transfer function because think about it in the signal flow graph terminology. If this is a loop, then what is the total gain here in this loop in the signal flow terminology? That's GSHS, right? Disregarding the minus sign here. So this is called the loop transfer function. Okay, this thing is the closed loop transfer function, and this is called the loop transfer function. Okay, and then you have forward path transfer function, which is just GS in this drawing. Okay, so these are the terminologies you might have to remember. All right, okay, and of course HS is the feedback transfer function. I think you know that, right? All right, yeah, loop transfer function or also the open loop transfer function. It's called the forward path transfer function, or just it's called the this one. Okay, for the open loop, or you can just call this, sometimes it's called OLTF, this one is called OLTF. So just to avoid any confusion here. Is the forward path transfer function. Okay, so this is sometimes also called open loop transfer function, but I don't call it open loop transfer function because in some terminology I have seen GS being called the open loop transfer function. In some books I have seen GSHS being called the open loop transfer function. But to avoid any confusion, I'm just going to call this GSHS the loop transfer function, because that's the terminology that we can use without any confusion. Okay, but in any case, okay, GS is the forward path transfer function, and this is sometimes called the loop transfer function, sometimes called the open loop transfer function. Okay, all right. So I think that's the definition is fine, right? All right, now we are going to define something else. Okay, what about this error signal? Since this error signal is a signal that appears in this system here, just like that, this can also be compared with respect to the reference input signal, right? So ideally, what would I want really? Ideally, I would want, after a certain amount of time has elapsed, I would want my control variable to match the reference input, right? So again, as usual, as I have been telling you, so this is what I want. So this is what I want, right? Right? This is what I want, and this is what I have. Eventually, after enough time has elapsed, I would want what I have to be equal to what I want, right? I would want to have what I want. Very simple. So essentially, after enough time has elapsed, I would want the reference input signal to be equal to the control variable in case HS is equal to 1. So technically, what I would want, I would want the error signal to become 0, right? I would want the error signal to become 0. So with that said, now let's define the error transfer function. What is the error transfer function? So look at this expression here. Okay, look at this expression here. So here we are writing ES equal to this, right? So let's just write this here, and let's just copy and paste this. So we are writing this, right? ES equal to RS minus CS times HS, right? Now I want to represent ES in terms of RS, right? ES in terms of RS, because that's my reference input signal, right? I want to represent ES in terms of RS. Fine, that's okay, but in order to do that, let's just see, let's divide both sides with RS. So I would have 1 minus, so if I divide both sides with RS, so I would have CS by RS times HS. But we already know what CS by RS is, right? So CS by RS is the closed loop transfer function, right? So that's GS by 1 plus GSHS. So GS by 1 plus GSHS, and that is now multiplied with HS, multiplied by. So with that said, so this becomes 1 minus GSHS, and this is 1 plus GSHS. And if we subtract this, do the simplification here, this becomes 1 plus GSHS, and on the numerator this simply becomes 1, right? 1 plus GSHS minus GSHS. So this is the transfer function of the error signal with respect to the input signal, right? So this transfer function, this is therefore I can say ES by RS. This is the transfer function of the error signal with respect to the input signal, and this is nothing but 1 by 1 plus GSHS, right? So this is known as the error transfer function. Error transfer function. All right? Right? There is no issue with this. I think this is completely clear, easy to understand, right? Right. Now here is a small problem. Okay, in this figure, really, when I said that what I want should be equal to what I have, or rather what I have should be equal to what I want, I kind of misspoke here, or rather I just slightly mentioned here that when HS is equal to 1, really this signal ES is called the actuating error signal. There is a reason for that, because here in the comparator, when the comparison happens, I am not really comparing my input with the output. I am not really comparing the reference input with the control variable. Instead, I'm comparing the reference input with some sort of feedback signal that is coming through this input here, that is coming through this input here, coming through this HS here, right? So ideally HS should be equal to 1, and for that, let me just again we are going to simply elaborate everything, and we are going to generalize all these things. So if I say HS equal to 1, so we're talking about unity negative feedback. Now we have a proper situation. Now we can say that our system looks like this. We have a comparator here, and this is the input signal, and that's RS. And now here we have the plant or the system or everything that we had combined into a single transfer function, I would say. That's GS, and this output has to be CS, right? Now what if I feed this back to the system without any modification here? So essentially HS is equal to 1. Then what we are doing, we are directly comparing the reference input with the output here. Then this signal is no longer the actuating error signal, but instead this is called the error signal. This is just the error signal now. So error signal is essentially the difference between the reference input and the output, okay, or the control variable here. I don't understand. And sometimes in some literature, to distinguish between error and actuating error is sometimes represented with EA, E with a subscript A. Okay, I don't write that. I just represent everything with E. E means whatever is fed from the first comparator here. Whatever comes out of the comparator is E, at least in my book. All right, so that's fine. That's the error signal. Okay, I think there is no confusion with this, because the thing is, why did I start with HS to be not equal to 1? Because I wanted the generalized expression, right? Because now I can easily put H equal to 1 in this expression and get the error signal from here. So the error transfer function, simply ETF, okay, that is error signal, ratio of error signal with that of the reference signal when the initial conditions are 0. Okay, that simply becomes, here in this equation just put H equal to 1, so that simply becomes 1 by 1 plus GS, right? Right, so that's not an issue. I think that's fine, right? Now why did I just derive all these things? Why did I spend half an hour deriving all these things? Because technically, try to understand that if this is my if this is the definition of my system, then what do I really want? I want the system to behave in a way that after enough time has elapsed, or after I have given it enough time, that the reference input matches with the control output. Okay, so whatever is the output actually matches the reference input, right? So if it's a temperature control system, and if I set the temperature to 80 degrees Celsius, then I want the output to reach 80 degrees Celsius, right? I want the error to become 0. Technically, if it's, for example, if it's a temperature control system, and if I set the reference to 80 degrees Celsius, I would want the output to become 80 degrees Celsius. Of course, I would have to give it time, but after I have given it enough time, I would want that to have 0 errors, right? So ideally, I would have the system to have 0 error, right? After enough time has elapsed. And the moment I say enough time has elapsed, I mean steady state. After the system has reached steady state, once I have given it enough time for it to reach steady state, then I would expect the reference input and the control variable to match. Okay, I would want the reference variable and the control output to match, because there is no feedback here, there is no feedback transfer function. Essentially the feedback transfer function is 1. So this error signal needs to be 1. technically, right? So this is something that you have to understand at this moment. Okay, so I want to see that this error transfer function, or rather from this, if I say es, then es is nothing but 1 by 1 plus gs times rs. Again, just remember that we are considering this special case here. We are considering this special case where hs is equal to 1. Okay, so that's the error signal. Okay, so ideally what would I want? I would want the system to behave in a way, that this error signal becomes 0 after long time has elapsed. So essentially I would want the error signal, keep in mind that the error signal is not es, okay, it is et. Okay, the error signal is et. Now in some books you would see that this is written as just et. I don't write e like this because this is a special character, right? This is exponential, whatever, right? So I would just write epsilon here. Okay, some books would write epsilon e, whatever, right? So I would write just epsilon. So essentially I would say the Laplace transform of the error signal in the time domain would be es, right? In some books you would see e. Okay, so again, don't worry about that. Okay, so I would want the error signal et to become 0. I would want the error signal et to become 0 as time approaches infinity. So as I give the system enough time to settle down, I would expect the error signal to have reached a 0 value. So essentially I would want this, when limit t tends to infinity, I would want the error signal, of course the time domain value, yeah, I want it to become 0. So this is what we are trying to look for today. Okay, we are trying to figure out under what situation we can expect something like this to happen, under what situation we cannot expect something like this to happen, right? What are the situations under which this would happen or this is guaranteed to happen, and under what situation this is not guaranteed to happen. Okay, so and that would be the system types. Okay, the type of the systems would determine whether or not we can guarantee something like this to happen. And again, there is something very important to remember. Whatever we are going to discuss today will entirely depend on the assumption that the systems we are discussing are stable. Okay, so every system that we are going to discuss today, everywhere we are going to assume that the systems we are discussing are stable. Okay, anywhere if somehow an instability appears, we cannot discuss those systems. So let me just preface this entire discussion with a word of assumption. So our assumption here, all systems, and the moment I say all systems, I essentially mean all transfer functions. The closed loop transfer function must be stable, the open loop transfer functions must be stable, the forward path transfer function itself must be stable, the feedback transfer function must be stable. Everything individually and combined, they all must be stable. Okay, all systems and also transfer functions essentially must be stable. So that's kind of the discussion, kind of the assumption here. Okay? In today's class, that's going to be the assumption. Okay, default assumption. So if anytime some one of the parts is unstable, really, if anytime the system is unstable, especially in the closed loop, then we cannot talk about errors at all, right? If you have an unstable system, it is never going to reach steady state, and there won't be any question of talking about errors, how far away the response is. Really, there won't be any point talking about that, right? So now let's take a very simple first order system. And define. So a very simple first order system. Let's define that. Again, unity negative feedback I'm considering, and later on we are going to elaborate everything, or rather generalize everything into feedback systems that have non-unity feedback transfer functions. As we could have many things here. We're just combining everything into just GS, right? And this is the controlled variable, controlled output, and this is the feedback. Got it, right? So we have that. Again, this is ES. All right. So now let's say here, let's say the transfer function GS in this one looks somewhat like K divided by tau S plus 1. Okay, that's kind of somehow that's kind of the way you represent first order transfer functions, right? So this is the final value of the response. So this is going to be the final value of the response of the open loop system, or the for transfer function itself. Okay, so this is the gain of the system essentially, and tau is the time constant. Again, this is how we discuss first order transfer functions, right? If we have any first order transfer function like this, that can be actually written in this form, right? Very easily, I think, right? So that's the transfer function we are choosing today, okay, for this one at least. Okay, so we're choosing this transfer function, right? No issues there, I think. All right. So now what is the error transfer function? So what is the error transfer function really? The error transfer function looks like this, right? Here, with this transfer function, what is the error transfer function? Again, see, I have given you GS. So error transfer function would be, so the error signal would be 1 by 1 plus GS times RS. And I already know the value of GS, so let's put that there. Okay, 1 plus K divided by 1 plus tau is 1 times RS. So now that's fine, right? Now let's discuss something important here. Now here I want to see whether the input, whether the error signal reaches 0 as time goes to infinity. But there is just a small problem. The problem is that I do not really know about the reference signal here. I do not really know about the reference signal. What kind of reference signal is this? Okay, what kind of reference signal did I put here? Okay, now let's talk about reference signals, and then we are going to come back to this, right? So we are going to essentially talk about 3 different types of reference signals today. Okay, and again, we discussed all these things earlier, I believe, right? So the 3 different types of reference signals that we are going to discuss are the unit step signal, which is, so unit step signal would be essentially ut, okay, and its Laplace transform would be 1 by s. Okay, then we would have unit ramp signal, essentially written as RT, okay, and that's just equal to TUT, and these are the Laplace transform of 1 by s square. And then we have unit parabolic signal, unit parabolic input, that's essentially half g square ut, and that's 1 by s cube. All right, the Laplace transform, here we have the Laplace transforms here. Okay, so if I draw them in the time domain, you know what they look like, but then again, let me just redraw them once more. Okay, so this is the unit step signal. Unit step signal remains 0 before time was equal to 0, and at time equal t equal to 0 we have a discontinuity and the signal jumps to 1. Okay, so that's the unit step signal. So this is 1 and this is 0, and time is 0 here. This is time, this is your ut, right? All right, again, this is just going to be a recap because I'm assuming that you people know about all these things already, right? Now this is the unit ramp signal. The value of the signal would once again be 0 as time t is less than 0. and at t equal to 0 it is also 0, and then it runs with a slope of 1, right? Runs with a slope of 1. So this is a slope 1 signal, and that's why it's called a unit ramp. This is called the unit step because the height of the signal is 1. It's called unit ramp because the slope of the signal is 1. So I'm saying slope equal to 1. So after 1 second elapses, the magnitude of the signal becomes 1. After 2 second elapses, because someone is saying how to contact me. I am going to write down the contact email here. Hold on for a second. This is my contact email ID. Just get in touch. Okay, email me there. Let me just write everything in capital letter. TDG @ okay, send me an email there. Okay, again, so as time elapses, so after each second the magnitude rises by a value of 1. So this is your ramp signal. Again, this R has got nothing to do with the reference signal here, right? And this is the unit parabolic signal, and let me just draw it once again. And here again, once again, since ut has been multiplied with all of these things, essentially this means that this multiplication with ut, here we have ut multiplied, it essentially means we are turning the signals into causal signals. So the value of the signal would be 0 before time is equal to 0, right? And this would be a ramp signal. Essentially it would be this would be a parabolic signal. Okay, so essentially the slope will keep on increasing, right? So that is how the signal looks like. And this is going to be pt, essentially half t square ut, right? Now there are other names of these signals, so I'm erasing this. Okay, all right, so there are other names of this signal. For example, now try to think about this signal in like the very fundamental mechanical way. Okay, if so the horizontal axis is time, if the vertical axis is distance, okay, or displacement, okay, displacement or distance, then essentially this is representing a fixed position, right? So before t was equal to 0, your position was 0. Now after t equal to 0, your position is 1, right? Your position is 1, and the position remains 1. Position or displacement, rather, your displacement is 1. Sometimes because of this reason, this is known as a position input. A step input is also known as a position input, because if I think about the output as position here, then this is representing a constant position with respect to time, right? So as time was less than 0, the position was 0, but at time t equal to 0 and greater than 0, the point is actually at coordinate 1 or something like that. Okay, so it's a fixed position here. Okay, it's called a position input because of that. Similarly, this is called a velocity input. So unit ramp is also known as a velocity input, because try to understand, if this is position, this is representative of position. So if the vertical axis is representing a position, then what happens here? Here what happens is that with time the position changes and increases, right? When time t is equal to 1, the position is also 1. Okay, when time t is equal to 2, the position is also 2, maybe something else. So as the time increases, the position also increases with a certain fixed constant value. So that is something that can be considered to be a constant velocity, right? So if I have an object that with respect to time is traveling, or rather traversing equal distance with equal spans of time, right? So if every 1 second it is traveling 1 unit of distance, right? So that way we can call that a constant velocity input, right? So it's called, this one was a position input, this can similarly be a constant velocity input, right? And the same way, this one, or unit parabolic signal or a parabolic signal, is a constant acceleration input. So constant acceleration input. So essentially the velocity is increasing, but the velocity would be increasing at a constant rate. So that's the acceleration input, right? So these are the three types of input that we are going to discuss today. All right. So with that said, let me erase this point here and see, that was the error. That was the error signal, right? That was error signal, and forget about the type of system here. Okay, we are going to explain the special types of systems shortly, right? So now, say this is the error signal. What do I want to figure out? I want to figure out whether the error as time tends to infinity becomes zero or not, whether this happens or not. That is exactly what I want to figure out, or rather I want to figure out the condition under which this happens. I want to figure out the condition under which this happens. So this is essentially E infinity, E at time tending to infinity, right? So just like that. So this is also a representation, right? We can write something like this. We can write with more mathematical integrity here. We can write any of these. So I want this to be 0. So we want this to be 0. Very simple. We want the error to become 0 as time goes to infinity. So essentially, after I have given it enough time to settle down, after the system reaches steady state, I want the error to become 0. After the system reaches steady state, I want the error to become 0. So I want the steady state error to become 0, right? So E infinity is known as the steady state error. Okay, so this is the error when the system has reached steady state. Again, I am considering the system to be stable, otherwise there would be no question of steady states at all, right? So this E infinity is known as the steady state error. I would just write SSE. Okay, so E is the SSE, steady state error, right? E infinity is the steady state error. So right, just like that, right? And someone has already guessed it right. Yes, we are going to use the final value theorem, because the only condition behind the final value theorem, applicability of the final value theorem, is that the system has to be a rational system. We are inherently assuming rational system, and the system has to be stable. Since we have assumed stable system and we are inherently assuming rational systems when we are dealing with transfer functions, final value theorem is applicable, right? If we find an unstable system, final value theorem won't be applicable. Okay, but since we are assuming rational systems and stable systems, final value theorem will be applicable. So I'm going to write this down. Since we are assuming that all the systems we are dealing with are rational and stable. Anyway, question, what is a rational system? Very simple. The number of poles or the order of the numerator can be at most equal to the order of the denominator. Okay, so of course transfer functions, so the polynomials on the order of the numerator's polynomial would be at most equal to the order of the denominator's polynomial. So if the denominator's polynomial is of order 4, then the numerator's order can be at max 4, not more than that. Then we call that system a rational system. If the order of the numerator's polynomial is higher than the denominator's polynomial, then we call that a irrational system, not rational system rather. For those, the final value theorem won't be strictly applicable. Okay, and if the system is unstable, then final value theorem is not applicable at all. Okay, now since we are assuming that all the systems we are dealing with are rational and stable, the final value theorem of Laplace transform which we actually derived in one of our earlier classes is applicable. See, this is an important point. Many teachers actually miss this point. The point is essentially is that we cannot blindly apply any tool that we have, right? We do not apply tools blindly, right? We have to understand whether or not we can apply it. So with that said, what is the value of E infinity? What is the steady state error? That can be achieved, calculated by calculating this using the final value theorem, right? So this is the value of this signal when time reaches infinity. So essentially that can be calculated by this. This is the final value theorem. This is the application of final value theorem here, right? So now we know, so this is steady state error once again. So this is the steady state error, SSE, right? So now this is a limit s tends to 0. Now s times, now we have ES. Now what is ES? ES is this. Let's bring it here. All right. So there is no problem with this, I think, right? And let me just do a small rearrangement here. So I would write this as limit s tends to 0. Okay. And I would write this as 1 by 1 plus gs times s times rs. Okay. So let's just keep that in mind. That's the steady state error. Okay. So now let's consider special cases. Okay. Let's consider special cases. Now consider this case where this transfer function or the for plus transfer function looks like this: k divided by tau s plus 1. It's a simple first order transfer function that kind of looks like this. Okay. All right. Again, I'm just giving you very simple usual general cases, and you can, I mean, this is the standard formula here. Okay, I can give you any transfer function as long as the feedback transfer function is equal to 1. You can just apply this and figure it out, right? Not an issue whatsoever. So if this is it, okay, if this is it, then what is E infinity? Now I have a problem. Because E infinity is limit s tends to, so I have a problem. What problem do I have? I have I want to calculate E infinity, but I know E infinity is limit s tends to 0, 1 by 1 plus gs times s times rs. But unless I know about rs, I do not really know about what to do with this, because I know gs, right? I would also need to know the input signal, right? I need to know about the input signal. So under this condition, I would have 3 different possible inputs, these ones, right? So let's consider the step input first. Okay, let's consider the possibility where it is a step input first. It is a step input, right? Let's consider that possibility first. So we are considering rs to be 1 by s. So I'm considering unit position input. Instead of saying unit step input, I'm saying unit position input. Okay, and there is a reason why I'm using these names, especially here. Okay, so with that, if that is so, then I can write epsilon. Okay, you can just elaborate this a little bit further. Okay, this is going to be limit s tends to 0, and this is 1 by 1 plus k divided by tau s plus 1 times s times rs, right? We understood, I think. We just put the transfer function, and here E infinity, the steady state error, is going to be this limit s tends to 0. Now let's just put the values. Limit, let's just write down everything. S tends to 0, 1 by 1 plus k divided by tau s plus 1 times s times, now what is rs? Rs is 1 by s. Okay, now see, notice very carefully that these can be cancelled, right? These can be cancelled. So now if I calculate the limit, so let's put s equal to 0. Okay, I can put s equal to 0 happily, because that is not resulting into 0 by 0 or any indeterminate form. Okay, if I put s equal to 0, then this denominator, this part becomes 0. Okay, and I am left with 1 by 1 plus k. I am left with 1 by 1 plus k, right? So that's the limit here, 1 by 1 plus k. and that's the steady state error. That's the steady state error. Okay, all right. So for a unit position input, that is the steady state error. Okay, just let's keep on calculating here. I'm going to keep a certain space here. Okay. Again, what do these things mean? I'm going to explain. Okay, let's consider another input where the input is the Laplace transform of the input is 1 by s square. So we are considering unit velocity input. So essentially unit ramp input. So if I choose that, then my epsilon infinity, that becomes limit s tends to 0. Same thing, 1 by 1 plus k by tau s plus 1, okay, times s times, now instead of rs to be equal, instead of rs being 1 by s, now this is 1 by s square, right? Now this is 1 by s square. Now I can cancel out one of the s's and just do a little bit of simplification here. S tends to 0. So if I cancel out one of the s's, there will be one s remaining here. And if I just put that here, so this becomes s plus ks times tau s plus 1. Now if I put the limit here, then what happens here? I can actually try to see. If I put s equal to 0, no problem. So this part becomes 0, right? I just multiplied these and combined everything here, right? So if I put s equal to 0, then this part becomes 0. But then I have 1 by s, right? So and that leads to infinity. So this is actually infinity, right? So this is actually infinity. Okay, there is also impulse input, right? There is also impulse input. Someone is asking whether there are other inputs as well. Yes, you have other inputs, but you will see that discussing these will be sufficient, because once you have a concrete understanding of these, any other inputs can be considered. But except there is another input, which is the impulse input. But since with impulse input you cannot really talk about, you cannot really consider impulse to be reference signals, right? In order for a signal to be a reference signal, that signal will have to stay there for in a sense for the system to reach a steady state, right? But an impulse signal really stays there at time t equal to 0, but after that there is no existence of that signal anymore, right? That signal becomes 0 essentially. So there is hardly anything that you can compare with, right? So whenever we are talking about errors, we do not really use impulse signals for our discussion. Okay, we use step, we use ramp, we use parabolic inputs, and if you consider higher inputs, for example quartic signals or quintic signals, those things can be used. But again, the discussion we are limiting the discussion here, because this is kind of what we really use, right? Either we accelerate, for example, consider a vehicle, right? Either we want it to reach a position, or we want it to go at a certain velocity, or we want it to accelerate, right? There would be hardly anything more. And let's consider the third situation. I believe you already understand the third situation if you have understood the second situation. We are considering rs to be equal to 1 by s cube, which is the unit acceleration input. Okay, unit acceleration input. And if you just calculate this as the same way, this is going to be s cube here, you would see that epsilon infinity is also here infinity. Okay, just do the calculation yourself. I think you can do this very easily, right? Just write 1 by s cube here. Same thing, it will be s square. This part will become 0 if I put the limit, but I would then have 1 by s square. That would lead to an infinity here, right? So acceleration input here, that also gives me an infinite error. Okay, so now with that said, I can now say something important here. For this kind of system, a system that has a transfer function like this system would have a finite steady state error if the input is a position input. Okay, it would have infinite steady state error if the input is a velocity input, and it would have an infinite acceleration error, steady state error, if the input is an acceleration input. This means that this system okay, in the closed loop can follow a position signal, okay, but with a certain amount of error, right, with a certain amount of error. But this system cannot follow a ramp input because it will result into infinite amount of error, and this signal will also not be able to follow an acceleration input because that would result into an infinite error. Okay, what I mean is that for this kind of a system, okay, in the closed loop for this kind of a system, okay, this is going to happen. This is what is going to happen for this system. Okay, now look very carefully. Try to understand that this is the reference input. This green one is the reference input, okay? And these are the value of 1. So technically in the steady state, what do I really want? In the steady state, I want the response of the closed loop system to reach this value, right? Response of the closed loop system to reach this value, okay? So this is RT, okay? But now unfortunately what would happen with this, there will be this much amount of error. There will be this much amount of error. So what does it mean? It means that in the steady state, again, you people know how the response of a first order system looks like. So if I draw the response, so again, causal system, so response would be like this. So in the since it's a first order system, and in the closed loop, the response would look like this, and it reaches a steady state here. So it has reached a steady state. But in the steady state, let me just draw the steady state properly. Even after the system reaches a steady state, if hold on, even after the system reaches a steady state, okay, this system has already reached a steady state, and this is the output here. There is going to be an error. So this difference, this gap is the error. When the system has reached a steady state, this gap will remain between what I want and what I have. Okay, so this is the output. The CT is the output of the closed loop system. RT is the input to the closed loop system. Input means the reference input. This is what I want from the system in the steady state. But in the steady state, the system would only be able to reach this much, and this gap here would be exactly equal to 1 by 1 plus k. This gap would be exactly equal to 1 by 1 plus k, because that's the error. That's the value of the error. Okay, that's the value of the error. Again, I am going to request you to not to mug up these formulas, because yes, actually in real life you would encounter different situations. So only try to remember the idea here. Okay, only try to remember the idea. Don't try to mug up any formula here. Okay, so that's the position input. So I wanted it to reach a certain position, but it failed to do so. So this system failed to reach a certain position. I wanted it to reach a position of 1, but it reached only a position that was this much apart. That had an error of 1 by 1 plus k. So of course you can figure out how much it went, right? So the final value of CT would be 1 minus 1 plus k, obvious. Okay, in a very simple fashion, if I wanted it to reach a value of 10 here, this would simply result into an error of this 10 by 1 plus k. Very simple. You can just put the expressions here accordingly, that way. So essentially that will be 10 by s, and the calculation will be automatically following from that. So that will be the error here. Okay, so whatever it is, you can understand, I think, right? So this system kind of fails to follow, or rather fails to follow a step request correctly. So I requested the system that it follows a step input. Unfortunately, it failed to do so, right? It failed to do so, right? So what would you think, what do you think would happen for a system that couldn't even follow a position command? If I ask the system to follow a velocity command, so if I ask the same system to follow a velocity command, so this is what a velocity command looks like. So essentially a ramp input. So this is my desired input, desired output. The input is the desired output. Always remember that, right? The input is the desired output. So this is the desired output, right? So this is the ramp signal. Okay. Again, this is called position command. Position command or position reference or position signal, position input, whatever. I'm gonna say position command. So the system couldn't follow a position command. This is now a velocity command. I want the system to follow a certain velocity, right? I want the system to reach a certain velocity. Okay. Unfortunately, what would happen if you just calculate the response of this system, you would see that for this system, the response, unfortunately, this is going to be very hard for me to draw. Still I can draw it, I think. Okay, again the output will be 0 at this point, 0 here, and then something like that. Okay, so the error will kind of keep on increasing, right? The error will keep on increasing. So you can understand, if I talk about the error here actually keeps on increasing, right? The error here keeps on increasing. I think you can see that, right? The error here keeps on increasing. As the time goes on, the error keeps on increasing. So this is what the response of the system looks like. So this is what CT is. Okay, this is what the response of the system looks like, or would look like if I ask it to follow a ramp input, right? So it would keep on increasing. The response output will also keep on increasing, but albeit at a slower rate. So, and that slower rate would result into a fact that this system would never be able to follow this input correctly. So as the time goes on, the error will keep on increasing and increasing and increasing. So here, as the time went on even further, the error even increased, right? So here, that is why we are saying that the error, so again, try to understand that the system has reached a steady state. Okay, but unfortunately the error is still going to be infinity. Okay, now here, since the input is a ramp signal, in the steady state the output is also going to be a ramp signal. Okay, in the steady state this output here is also a ramp signal, so this will be a constant slope. Okay, but this slope will be lower than this slope. So essentially the velocity here will be lower than what the velocity we have here. So that is why we are saying the velocity to be like this. Now of course, for acceleration you can just understand that a system that could not follow a position command properly will utterly miserably fail to follow a velocity command. And if I ask that system to follow an acceleration command, then you know the rest, right? It won't even come close to following that acceleration command. So there is no point of drawing that, I think. Okay. Okay, try to understand the idea here. All right. Okay. So systems that that have this kind of a feature is known, and let me just write it down. Very similar thing, and something very similar would happen for acceleration command. All right. So this system is known as a type 0 system. Okay. A type 0 system is a system that can follow a position command with some error, with some finite error, but cannot follow a velocity command or acceleration command at all. Yes, someone has already got it right. If I have a system that has 0 velocity error, okay, it indicates that it will have 0 position error. Yes. Okay, and someone is saying that for the first graph the input is ut. I'm not writing RT in the sense that this is a ramp signal. I'm writing RT to refer to the fact that this is the command signal, this is the input signal. Okay, I'm writing RT to mean that it is the input signal. Okay, I'm not writing it as a ramp signal. I want to mean that it is the input signal, reference input signal. Okay, inverse Laplace transform of RC. Okay, I think you got this, right? So this type of system is called a type 0 system. Okay, so now let's consider another type of transfer function, and that would obviously be a type 1 system, and you would see how. Again, just keep in mind that we are only considering the forward path transfer function here, the forward path transfer function. I do not really, I'm not talking about anything in the feedback path. We are considering the feedback transfer function. So this is now a type 1 system. This is now a type 1 system. Okay. Now a type 1 system, and look very carefully. Okay, I will allow you to notice later on. Okay, a type 1 system has a very special kind of transfer function. Okay, so let's just do the same calculation once more. Okay, let us just do the same calculation once more. So I would happily copy and paste everything. I would happily copy and paste everything, and I would allow you to notice what type 1 system actually means. Okay, so that's fine, right? I'm just going to write an S here, right? That would do, right? I did not change anything, and let's just also copy the calculation here. Okay, so now we have an S here. All right, so now of course that much is fine. Now what about now? What about now? If I just do the calculation here, now if I put S tending to 0, what happens? What happens to the limit? So I am actually calculating this limit S tends to 0, 1 by 1 plus. So if I put this, so if I put S equal to 0 here, I can do that. So that becomes K by S. I think you can see that, right? But now putting S equal to S tending to 0 eventually makes this an infinity, right? Eventually makes this infinity. And in the, so that's essentially 1 by a very large number in the denominator. 1 divided by a very large number in the denominator eventually gives you 0, right? For this system, so this system has a 0 error to unit position input, right? Or rather any position input. So if I give this system a position command, then it will be able to follow that position command properly. Given enough time, this system will be able to follow the position command properly, right? I think that's understood, I think. Okay, so let's now copy paste the next calculation here. So unit velocity command. Okay, let's copy the unit velocity command and check the calculation here. Okay, so that's my unit velocity command here. Okay, and here only the calculation will differ in the sense that I would have a S multiplied here. Okay, just write it properly. So I would have 1 by 1 plus K times S tau plus 1, and then I would have S times 1 by S square, right? And let's see the calculation here. So I would have one S here, so I would have another S here, right? Thanks to the transfer function. Now let's see the calculation. So here this S and this S can cancel out. So I would have limit S tends to 0, 1 by S plus K by tau S plus 1. All right, so now if I do the calculation here, so you see I can put S equal to 0 here, can I? Yes, I can put S equal to 0 here, and I can also put S equal to 0 here. So eventually this limit actually becomes 1 by k. To see, I put s equal to 0 everywhere. I can do that because it does not result into an indeterminate form. Now here I can see that it can follow the unit velocity input, but with a fixed error, okay. And if I now also copy the, again copying pasting, right, if I now copy paste the acceleration input, or rather let's just do the acceleration input, copy this part, okay, let's copy the acceleration input for this, okay. So here the calculation would be very similar to this, except now I would have a cube everywhere. For the acceleration input, that's going to be 1 by ss cube. That's going to be 1 by ss cube, right? So I do have 1 by ss square here now because of this ss cube here. Okay, I do have 1 by ss square now here. So again, after doing the simplification, I would have 1 by s here, and that would actually give me 1 by 0 here, right? So, and eventually that would result into an infinity. Just if we just simply calculate the limit. Oh, sorry, that would result into an s in the numerator. Sorry, I did miscalculate here. If I do the calculation here properly, this becomes s square here. So this becomes 1 plus k s square divided by s times s tau plus 1, and that gives me ks really here, right? So if you put s equal to 0, then this becomes 0, the denominator becomes 0, the entire denominator becomes 0, and when the denominator becomes 0, this becomes infinity, just like that. All right, so now for this system, for this type of the system, we have this situation. Okay, if I give this system a position command, okay, again, what is the position command? Essentially a step input in the reference, right? So this is t. If I give it a step input in the step input, just like the previous example, okay. So this is the reference input once again. So this is my rt, okay. So this is the position command, okay, and again 1. So in the steady state, I expect the response ct to reach the expected in my output, right? So again, reference or the command signal is the expected output, right? I want the output to reach that value, and it will indeed reach this value for this particular scenario. So the response could be oscillatory, since it's a second order system now. The response could be oscillatory or something else, but the point being, it is going to be say it is going to reach this steady state. So the response could look like this, could be oscillatory, but the steady state error is going to be 0 no matter what. Okay, the response could be something like this, or whatever it is, the steady state error is going to reach this. Even this could be, this could get a bump in the opposite direction and then still reaches that. Okay, the point being, the steady state error has to be 0 when I ask it to follow a position command. Okay, so here I would say, safely say that E infinity will be equal to 0. Okay, but what about what if I ask this system to follow a ramp input? So essentially, what if I want ask it to follow a certain velocity command? What if I ask it to follow a certain velocity command? Okay, so let's look at the command signal. That is what the command signal would look like. And again, so this is the velocity command once again. So this is RT again, and this is the velocity command. All right, velocity command. And here, say the response is slightly oscillatory, just like that, and maybe the response looks like this, 0 here, and it will oscillate first, And okay, it did me a favor. Now, this is the response of the system. Again, it has reached a steady state. The last graph here. Okay, the response here, okay, for different systems, for different values of the parameters k and tau, the response could be oscillatory, response could be like that. Okay, but the point is, then when the response reaches steady state, when the output reaches steady state, or when the CT, essentially, which is the control variable, reaches the steady state, the error must be zero. Error would be zero, because that is what we have derived here, right? Mathematically speaking, right? So we have derived that, and that is what it means here. So there would be, the response would reach a value of 1, right? If the input is 10, the response would reach a value of 10 in the steady state. Whatever it is, the response would reach that value in the steady state. Okay. Now here, if I give it a ramp input, then of course the steady state would mean that the system is, the response is having a constant slope here. But again, unlike the previous example where the slope was different, okay, so the gap was increasing, so the error was increasing, and eventually when enough time would elapse, the gap would be infinity. Now here, since the slope has become equal, okay, so after a certain amount of time the slope will become equal, but since there is a certain fixed gap here, we would say that the steady state error is there, but it is finite. So for this system, if I ask this system to follow a velocity command, it will be able to follow the velocity command with a certain amount of zero. Yes, someone is saying yes. So this, for this one, the steady state error will become zero no matter what, right? And here we are saying that E infinity is finite. But what is the value of E infinity? That's 1 by k. 1 by k, right? So we have that. So there will be always a gap between what I want and what I got, but that gap will not increase. That gap will not increase. The gap will remain the same throughout time, right? And for acceleration input, now I do have to draw the acceleration input. There is no other way. Really. For this system, if I, let me just draw the acceleration input signal first. Again, this is going to be a parabolic input. Now think about this system. This system is a system that could not follow, that could happily follow a step command. So a position command was properly followed. So I wanted the system to reach a certain position, it could reach a certain position, but it could not follow a velocity command. Okay, it could not follow a velocity command. Okay, so of course it could not follow a velocity command, but it could follow it with a certain amount of error, finite error. Of course, if I ask it to follow an acceleration, it would now fail miserably, right? So what would happen is that the response is now going to look like this. So it will not accelerate, but it will accelerate with a different rate. Okay, so once again, as time goes on, the gap will keep on increasing and increasing and increasing, and thus the E infinity here, this is the gap here. Okay, so I would say E infinity here will reach infinity for this system, right? Eventually, as this happens. So here RT is the acceleration command, right? So it won't be able to follow an acceleration command properly, right? I think you people got this, right? The very simple thing, a system that couldn't follow a velocity command would fail miserably in following an acceleration command, right? Just like that. Okay. All right. So I think that's understood. Okay. So this is called a type 1 system. Type 1 system. Again, just keep in mind we are only talking about the forward path transfer function. And now let's write down a type 2 system. And you might have already noticed what we are doing here. That's an S square. Okay, I think the S square is visible properly. Just make it bigger. Okay, so with that said, let us calculate everything, or I shall keep this calculation for you. Okay, you would see that for okay, you do the calculation for this one. Okay, so you would see that for unit position input for this system, I would ask you to do the calculation yourself, that for unit position input, epsilon infinity would be 0. For this system, for unit velocity input, someone has asked a question regarding, is there any type of system that would follow all signals properly? Yes, and you would be able to figure that out yourself soon enough. For this one, this is also going to be 0. This will be able to follow the velocity input signal properly. You can verify these yourself. And for the acceleration input, it will follow the acceleration input with a certain error, with a fixed or with a constant error. Here epsilon infinity would be 1 by k, right? So this has these errors, right? Now look at these systems very carefully. Okay, what do the transfer functions look like? What do the transfer functions look like? Again, there is just one small thing. While defining the system here, while defining the type 2 system, I really should use my brain to make sure that the system is stable. Really, this system, if I put this in the forward path and close this loop, this will be an unstable system because it will kind of violate the necessary criteria in the route table. So for my conscience, I'm going to write this as something like this. But again, the calculation will be the same. You can just do the calculation because you just, after all, you're just calculating the limits. Won't matter. Okay, all right. So all right. So essentially, you could see it yourself. If you just wrote this and close the loop, the system will always be unstable. Will always be unstable because the system will violate the necessary criteria in the route table. Okay. So that is something you can figure out yourself. All right. So now notice very carefully. We just defined 3 types of system. Type 0 system, that follows a position input with a fixed error. So let me just make a table here. Okay, let me just make a table here. Hold on. Bad. Nice. Nice. All right. Here I'm writing the system types here. So here I'm writing type 1, type 0, type 1, type 2. Of course, you can have type 3, type 4, type 5 systems, right? And I am considering position command, position input. So essentially unit step. Okay. Velocity command, so ramp, and acceleration command. Okay. So for this system, for these for type 0 system, the steady state error is 1 by 1 plus k. The velocity error is infinity, the acceleration error is infinity. For type 1 system, the position error is 0, the velocity error is 1 by k, the acceleration error is infinity. And for type 2 system, the position error is 0, the velocity error is 0, the acceleration error is 1 by k, right? All right. So now I am asking you your question back. So can I find out a system which can follow a position signal, velocity signal, and an acceleration signal without any error? So what type of system would actually have zero position error, zero velocity error, zero acceleration error? What type of system would have that? I think you can answer this question. So I'm patiently waiting for your answer, right? So apparently only very few of you are left. Yes, the answer is correct. Someone said type 3. Of course, type 3 system would be able to follow position signal, velocity signal, and acceleration signal properly without any error at all. Now, what is type of a system? Now, if I look very carefully, then for a type 2 system, as you can see, there are two open loop poles at s equal to 0. For a type 1 system, there is one open loop pole at type equal to s equal to 0. And for a type 0 system, there are no open loop poles at s equal to 0, right? So eventually with that we can say, so we can see that the type of a system is equal to the number of open loop poles at the origin. So we can see that the type of a system is equal to the number of open loop poles at the origin, right? So how many poles that GS would have at the origin? Someone is saying type 2. No. Type 2 system would have the acceleration error. Type 2 system would have a constant acceleration error. It would have zero velocity error, zero position error. Okay. So here is an important distinction. Okay, in many popular, or should I say, study materials and online classes, and many teachers as well would tell you that the type of a system is defined as the number of open loop poles in the origin, right? But it is not. Type of a system is defined through these errors. Okay, through what kind of errors they happen to have, right? Type of a system is not defined through what number of poles or number of poles in the origin, but type of a system is defined through these errors. Okay, so and it somehow just coincidentally is equal to the number of open loop poles in the origin. It is just like that. Okay, it is coincidentally equal to the number of open loop poles in the origin, just like that. Okay, so rapid round. I am going to write down a few transfer functions, and you are going to tell me whether they are you are going to tell me that they're types. Okay, order and type, let me just say. Okay, so again, all these are GS, so the forward path transfer function, right? So this is GS. Okay, tell me the order of the system and the type of the system. So this is question number 1. This is question number 2. This is question number 3. Just write down the order and type. I want the order and type, and any comments that you might have regarding the steady state errors. Okay, all right. This is a square. Someone is you are confused. I think you are confusing order and type. Order is the order of the denominator's polynomial. Here, for this one, what is the order of the denominator's polynomial? It is 5. If you multiply everything, the highest power of s would be 5. So it's a 5th order polynomial. But how many zeros do you have at, how many poles do you have at s equal to 0? How many poles would you have at s equal to 0? How many poles here would you have at s equal to 0? That is solely determined by this. See, this will determine how many poles we have at s equal to 0, right? So it is going to be a type 2 system, right? There is no order type 5 system. I have not given any type 5 system. So if you are saying type 5, you are probably confusing order with type. So order is equal to, not defined by, but equal to the number of open loop poles at the origin. The question is, how many open loop poles does this system have at the origin? How many open loop poles do you have at the origin? So how many poles do you have at s equal to 0? You have 2 poles at s equal to 0, right? This is that thing. Because of that, you have 2 poles at s equal to 0, and that's the type of the system, right? Similarly, this system is of order 4, because if you multiply the denominator's polynomial, you get 4. Okay, so you get a 4th order polynomial, but the order is 1 because you have only 1 pole at the origin. Same thing, it is that this one, the denominator's polynomial has is of only order 1. Okay, and the type is 0 because there is no pole at the origin. Here, for this one, the denominator's polynomial is of order 5, but type is 3. Take another example. Again, if this is the forward path transfer function, then its order is 2, but type is 0. No, you are confused, I think. Yeah, sorry, order 6, sorry. Yeah, it's order 6, right? Thank you. All right, so I think it's fine, right? All right. So now you can understand that that notion of k divided by something is not really that useful, right? So this table is not really that useful. This table is not really that useful, honestly speaking, because your transfer functions would not probably look that innocent. Okay. Okay, just one more question. One more question. Okay, what is the order and type for this one? What is the order and type? Okay, just hold on for a second. All right, so I think this is fine, right? So this is that kind of this the transfer functions won't be that innocent really, right? So we have to figure out something generalized. Okay, something generalized. So to do that, okay, again before that, again this is what is the order? Yeah, so this is order 3 and type 3, but there is just a small gotcha in all of these. Okay, this system is fine for most part. Okay, now there is a problem with this system. If you are thinking about the errors, right? Can you tell me what the problem would be? So this would be a problematic system in terms of the errors. Okay, so it's a type 1 system. You might expect the steady state error. You might expect the steady state error for this system for step input to become equal to 0, but that won't be the case. That won't be the case. Reason is that this system is unstable. See, in the polynomial here you have one of the coefficients missing. In this polynomial you have one of the coefficients missing, and because of that you can't even define errors. You can't even define errors. So even though the type is 1, all the errors would be infinity, and you can't even define errors really. Okay, it's an unstable system. So truly errors are defined only for stable systems. If you have an unstable system, you can't even define error. Okay, so you cannot say infinite error because you can't even define error. Okay, it's an unstable system. In a very similar fashion, this is also going to be an unstable system. Okay, this is also going to be an unstable system. So really speaking, this also does not have anything like that. And as such, I should really have had something on the numerator as well. Let's make this, turn this into something useful. Okay, something that actually does follow this. So tau 3 s plus, and that will be fine. All right, so again I'm just putting my best effort to make the system stable anyway. And here also we have another system that would be unstable, so there is no question of. So what are you saying? 0 is a square, what? All right, so if I go back to the very definition of this error, okay, we saw that the error signal, the Laplace transform of the error signal was equal to 1 by 1 plus gs times rs, right? Gs times rs. So essentially e infinity, sorry, 1 by es, right? Es, right? So e infinity would be limit s tends to 0 s es, right? And if I just put this here, limit s tends to 0 s times es, so es is this 1 by 1 plus gs. Now instead of looking at special cases, now if I look at this, then I simply have three possible scenarios. I have a step input and a ramp input and a acceleration input, right? For the step input case, step input. Now for the step input case, say for example I am considering any transfer function here. Okay, for the step input, now see e infinity is this limit s tends to 0 s times 1 by 1 plus gs times rs. Now of course for the step input rs is 1 by s, so that will cancel out. So I would have this, right? So limit s tends to 0 divided by 1 plus limit s tends to 0. So gs, but again only thing that is dependent on s is gs, so I can reduce this limit to this limit s tends, so instead of saying this I can say 1 divided by 1 plus limit s tends to 0 gs, right? Right? All right. Similarly, for the ramp input, or rather ramp input or whatever you want to call it, or velocity input, position command, say velocity command. Okay. So similarly, epsilon infinity, so error signal, value of the error signal when time reaches infinity. So after enough time has elapsed, 1 by s times this. Now of course rs is 1 by s square. So I have to have this calculation, limit s tends to 0. So one of the s's will remain 1 by s times s gs. And of course I can put the limit here. So if I put s equal to 0, that's fine. So I get 1 by limit s tends to 0 s gs. Okay, just keep these in mind. And for the other case, for the acceleration input, so parabolic input, e infinity would be limit s tends to 0 s times 1 by 1 plus gs times 1 by s cube. All right, and subsequently this becomes limit s tends to 0 1 by s square plus s square gs. So again I can put s square equal to 0, so this eventually becomes 1 by limit s tends to 0 s square gs, right? Right. Now of course depending on the situation it will be 0 or infinity, right, depending on the type of the system here, right? So now we can modify our table that we had earlier. Rather we can copy paste this table and make it a little bit better, because this table for the most part is kind of useless apart from very special type of systems. So now instead of saying this to be 1 by 1 plus k, I'm going to say this is going to be, for type 1 systems, this is going to be 1 by 1 plus limit s tends to 0 gs, because that is what we got. Of course these are going to be true, and this is going to be 1 by limit s tends to 0 sgs, and this is going to be 1 by limit s tends to 0 s square gs, right? So these are better terminology that we can use. Okay, I think this is kind of better. Now it is not assuming any special form of the transfer function, it could be any transfer function now, right? So this is kind of the special form here. Now these terms, now these very special terms, this thing here, this thing here, and this thing here, these very special terms have special names. Okay, again this thing here. Okay, so here these things have special names actually. Okay, so for any system, okay, for any system, limit s tends to 0, this thing, okay, s tends to 0 gs equal to the position error constant. This is called the position error constant. They have special names. This is called, the next one is called the velocity error constant. You can understand why. You can understand why, because this is related to error due to a velocity input, and s square gs, it's called the acceleration error constant. Okay, so these are the special names here. So now this table can once again be modified and be redrawn using those error constant terminology. So this is 1 by 1 plus kp, and again these are the definitions there. Okay, this is, again I need additional pages. This is 1 by kv, this is 1 by ka. All right, so this is what the steady state, this is how we define steady state errors. Okay, again these are all e infinities, values of e infinities, huh? Right, right. So far we have only considered systems that have unity feedback, right? What if the system does not have unity feedback? For non-unity feedback systems, so essentially hs not equal to 1. Okay, so for those kind of systems, so let me draw one of the examples. Say I have a system, oh I think I had drawn it, right? So let me just copy paste it. Yeah, this was a non-unity feedback system. Let me try it once more. Hmm. So how do we define error signal? Because I'm talking about error. Error is the difference between RS and CS. Unfortunately, for a non-unity feedback system, I never have RS minus CS, right? Because CS is fed back to a feedback element, and this is GS. Again, this is CS, this is RS, and this is now being fed back by a feedback element, by a feedback transfer function. Now this error signal is no longer the error signal, it is the actuating error signal, right? I have this actuating error signal here, so this is EAS essentially, right? This is the actuating error signal. I'm not writing EAS, just keep in mind, because this is no longer RS minus CS, right? So I cannot say I want this to become equal to 0, right? I cannot expect this to become 0, right? So let's just say EAS, say this is the actuating error signal. I want the error signal, but I do not want the actuating error signal, right? I want to do the same calculation, but with this, right? Now, unfortunately, whatever we have discussed becomes invalid the moment we have HS not equal to 0. But can we generalize our discussion to a discussion a bit so that everything that we have discussed is not does not become useless, right? So question is, can I turn this system into a unity feedback system? The answer actually is surprisingly yes. I can turn this system into a unity feedback system. Notice how. Okay, notice how. Again, the idea we are going to use right now is going to straight away come from our concept of block diagram reduction. I would rather say block diagram complication here. I'm not going to reduce it. I'm going to make it slightly more complicated. Okay. So now RS is there. Okay. This is ES. Now I want to keep everything intact. Okay. As long as the input and output are intact, everything remains the same. So what if instead of having HS here, what if I do something important, something slightly more ridiculous here? Say, what if I change this feedback transfer function instead from just HS to something like HS minus 1. Okay. And then I do something like this. Okay. Let us say HS Yeah, right. Then I take away another feedback from here and send it back. And now I just call this RS instead. Now see, these two systems are equivalent. These two systems are equivalent. Why exactly so? Let's see why exactly so. This is CS, right? So CS is feeding back from here. So I have CS here. So CS approaching this. So this is CS. So here in this point we have ES. ES is RS minus CS, right? That's fine. But here what is EAS? EAS is ES plus this signal. So this is my BS here, and here I can say BS is HS minus 1, or rather it will be plus 1. Hold on for a second. HS minus 1. No, fine. HS minus 1 times CS, right? That's BS. Now what is EAS? The actuating error signal. So the actuating error signal here would be ES plus BS, right? Sorry, ES minus BS. ES minus BS. Now here in this diagram, ES is, what is ES in this diagram? ES is RS minus CS. So this is RS minus CS minus, and what is BS? BS is this one. So this is HS CS minus CS. So BS is HS CS minus CS. And if you just do the simplification, EAS becomes RS minus CS minus HS CS plus CS, and these two CS will cancel out. This will become RS minus HS CS. So that's the actuating error signal here, right? This is the actuating error signal EAS. And here in this figure, that is the same, because what signal does go back in here? That's HS CS. So HSCS goes in, and what is the actuating error signal? EAS here is RS minus HSCS, right? Right? So this reference minus this feedback signal. So we haven't modified the integrity of the system. So the actuating error signal remains the same. Now, along with the actuating error signal, we have defined an error signal by doing this modification. These two are equivalent. These two are equivalent, right? Right? So we have modified this system into an equivalent system here, just like that. So let's now copy this. Let's now copy this and paste this and do some simplification on top of it. Okay, let's do some simplification on this. So now we have an error, a proper error signal, right? Instead of just the actuating error signal. Now you can see that this is a feedback loop, right? And we can do a block diagram reduction here, right? This is a feedback loop, so we can do a block diagram reduction. So this is equivalent to and here we are doing block diagram reduction here. So this transfer function after block diagram reduction becomes GS by 1 plus GS times HS minus 1. And that's it. So the unity feedback equivalent of that system is just this, right? So this is equivalent to, this is equivalent to a unity feedback system. This is equivalent to this, right? This is equivalent to this. These two are equivalent, right? So this system and this system, they are equivalent, right? So if I give you a system which is not unity feedback, you can convert this to a unity feedback system by doing this. Okay, by doing this. All right. Now here you had an actuating error signal. Okay, which is not exactly the error signal, but here you have a proper error signal, right? But these two block diagrams are equivalent, right? These two block diagrams are equivalent. So now we call this transfer function, we call this thing GES, GES, right? We call this thing GES. So now if this is the equivalence here, then this is equivalent to this, this is equivalent to this, where we have this simple configuration here. This is GES, I call it GES. So this is a unity feedback system where GES is this transfer function, right? So this is GS divided by 1 plus GS HS minus 1, GS times HS minus 1. So which is GS 1 plus GS HS minus GS. That's the GE. So if I give you a system which is not unity feedback in nature and ask you to calculate the errors, all you have to do is to calculate GES, and then you can calculate the errors as you did. Okay, you can then calculate the errors very easily. Now of course, with that definition, what would happen? What would happen to these tables? Essentially, if I give you a non-unity feedback system, then these tables can be simply modified by replacing GS with GES, because that is what we get when we convert the non-unity feedback system to a unity feedback system. So essentially I would write GES here, and GES here, right? So if I give you a unity feedback system, then no problem, right? If I don't give you a unity feedback system, then that's a problem, right? And again, the error constants are again defined exactly the same way, except for a non-unity feedback system, you have to first convert this to unity feedback system, and then of course the transfer functions, the forward path transfer function will become GES, and all these things will be like that. Okay, and subsequently we have the modified table accordingly. So the same thing, right? So this table will remain the same no matter what. This table will remain the same eventually, because we have redefined our constants here. Okay, so time for a small question. Again, ask any question that you might have. Any question? All right, so let's solve a problem, right? So if I give you a unity feedback system, no issues, carry on. If I give you a non-unity feedback system, then you have to calculate it accordingly. All right, so let's solve a problem with non-unity feedback. Okay, so question would be something like calculate the error constants. Just one more thing, these error constants are also known as static error constants. Okay, because they are error constants for steady states. Okay, so I would just mention the name here so that you don't forget. calculate the static error constants and steady state errors for the following system. All right. It might look like a type 0 system, but it is not. It is not. Because we have a non-unity feedback. Okay. Because we would have a non-unity feedback here. Hold on for a second. Let me find out a nice problem. Okay, let's make this S. Okay. So first question is, what is the type of the system? Again, I told you earlier that type of the system is not defined by the number of open loop poles at s equal to 0, because in that case the type of the system would be just 0 here, right? But the type of the system is defined by the steady state error, nature of the steady state errors. Okay, so in order to define the type of the system, I have to figure out the steady state errors, or we can redefine the system as a unity feedback system, and then we can figure out the type of the system. So okay, so if we redefine the system as a unity feedback system, again unity negative feedback system, then the forward path transfer function would be gs ges, that's equal to gs by 1 plus gs times hs minus 1. All right, so let's do the calculation here. So what is gs? Gs is 2 by s plus 3. That's 2 by s plus 3. That's 1 plus 2 by s plus 3, and that is then s minus 1. All right, hold on, I want this problem to be a slightly better one. Let me try my best to do this. All right, for our sake, let's make this all right, so let's make this 3 divided by 3. All right, so that would serve our purpose here. So the point I want you to take home. So this might look like a type 0 system, but it is not, because there is a non-unity feedback. So if I define the error forward path transfer function with when I convert this to a unity feedback system, then this is what it becomes, right? All right, and then if I do the simplification, actually the GS, someone is saying, is the GES related, the formula where we use GES is valid for any transfer function, any system where HS is not equal to 1. In fact, this is also equal, this is also valid when HS is equal to 1, because if HS is equal to 1, okay, then if HS is equal, hold on for a second, did I make a calculation mistake? Hold on, did I make a calculation mistake anywhere? Yeah, yes, right, no problem here. This formula is also valid when HS is not even equal to 1, because if you see, look at this formula here, if HS is equal to 1, then what is GES? If HS is equal to 1, then GES is just equal to GS, right? Because if HS is equal to 1, then this becomes 0, then I will have GS by 1, so GES will be equal to GS. So you can imagine this is the ultimate table here. These are the ultimate tables, these are the ultimate error constants, because if HS is equal to 1, then GES will become GS, just like that. Okay, and if HS is not equal to 1, then this is GES, right? So these formulas are valid always. All right, so we have that then. So again, I need additional pages. So with this, let's simplify this. So I would have so that's E divided by S plus 3 plus PS plus 4S. Okay. I think that's 3 by 4S, right? If I'm not making any gruesome mistake here. Right. That's GES. So GES is 3 by 4S, right? Just 3 by 4S. Okay. So that's GES. So I would say that this is the type. So this is type 1 system. Type 1 system. This is a type 1 system, right? Very simple, because GES has one open loop pole, one pole at S equal to 0, right? So this is a type 1 system, even though it looked like a type 0 system. Okay, hold on for a second. So this looks like a type 0 system, but it is not. Okay, it is not, with double exclamation signs. It looks like a type 0 system, but it is not, because if you calculate the forward path transfer function after you turn this into a unity feedback system, this is what you get. Okay, and that's a type 1 system. And by nature, we know for type 1 system, a type 1 system will follow, will be able to follow a step input correctly. Okay, got it? And so if I ask you to calculate the errors, so now the error constants, so the position error constant would be limit s tends to 0 GES, right? And the corresponding steady state error for step input is going to be 1 by 1 plus kp. Okay, and the velocity error constant is going to be limit s tends to 0 s ges, and the corresponding steady state error is going to be 1 by kv, and acceleration error constant is going to be limit s tends to 0 s square ges, and the corresponding error is going to be 1 by ka. It's a type 1 system. We know that this is going to be 0, but let's verify that. It's a type 1 system, so let's verify that. So if I calculate this limit, what happens to this? S tends to 0 ges. What happens to this when s tends to 0? This becomes infinity, right? This becomes infinity. So the position error constant is infinity. So the position error constant is infinity. And since the position error constant is infinity, this is going to become 0, right? And here for this one, if I multiply ges with s and then calculate the limit when s tends to 0, that becomes just 3 by 4. So the velocity error constant is a finite value, and of course the reciprocal of the velocity error constant is the error, steady state error due to a ramp input. That's going to be 4 by 3. And here this is going to be 0, because if I multiply this with s square and take the limit when s tending to 0, that becomes a 0, and subsequently this becomes infinity. So this is just behaving like a exactly behaving like a type 1 system, right? Even though this was originally the forward path transfer function, by just looking at that you would see that this is a type 0 system, so this should really have a certain error in the forward path, right? Certain steady state error. But by making a suitable feedback, we can turn this system into a type 1 system that has 0 position error. So this is again another feedback element, feedback design, where we choose our feedback elements in such a way that that overall system behaves slightly differently, right? So if this is position, if I am feeding this position, then this is also position, right? If the input is a position input, then output is also a position output, right? But what is the feedback? What is s? You already know that multiply a signal with s essentially means we are differentiating the signal. So what we are essentially feeding back here is velocity, right? So we are differentiating the position output and feeding that back in. So we are feeding back velocity. So we are feeding back velocity, and by doing that we are actually making sure that the system is capable of following the position properly. Okay, we are making sure that there is 0 position error by feeding back velocity. So it's a velocity feedback, often also known as a tachometer feedback for your position control systems using motors and everything, right? When you feedback using a tachometer, a device that measures velocity, then you essentially have a velocity feedback. Okay, and with that, if you have a tachometer feedback properly, you can actually do a proper position servo mechanism. Okay, essentially you can follow position commands properly. Okay, just to understand what the particular discussion here. Got it? But if this was a position feedback, so if this was something like 1, that would be a position feedback. It could be any other constant, that would be a position constant, position feedback. And if it was a position feedback instead, in that case it won't be able to follow that step signal. Okay, follow the position input signal. I think that concludes our discussion. Okay, you would get a long list of exercises to solve with this, so don't worry about that. Any question if you have, please ask. Right, so if you have any query. So we have discussed quite a lot today. and we didn't have to write any computer program because I have drawn everything by hand, right? All right, so if you don't have any queries, we can end the stream today, and probably I'll see you tomorrow. Okay, we have questions about the root locus. Okay, yes, we are going to have a, a discussion using Google Meet, right? To discuss issues using issues with root locus, right? Because intentionally I gave you problems that you wouldn't be able to solve without a little bit of hint. Okay, actually, right? So again, you would see that the hints are pretty obvious once you learn those. Anyway, so again, yeah, we're going to have a discussion there. Don't worry. So all right. So thank you very much. I will see you tomorrow. Stay safe.